we start looking at we'll do an experiment, a thought experiment, and try to see what happens. And what we will do is this. We will look at a system where we have a cylinder piston arrangement, and in that we have a substance which we will say is water at ambient conditions, 1 bar, say 310 K. And what we will do is, we'll figure out, say, okay, now I'll keep on heating it. After heating it sometime, we'll stop so that there is equilibrium, and then ask the question, the pressure I'm going to keep as 1 bar, what is the temperature? That's the first question. The second question is, what is the state of the substance or the state of water inside this? So what we are doing now is what we call isobaric heating. Okay, the first case, we do a little bit of heating, and we know from experience nothing much is going to happen. Water expands a little bit. Thermal expansivity of water is something we have learnt in school. That comes into play, and because of that, this water has expanded a little bit, and say it has reached, say, from 300 Kelvin, say about 30 degrees C, it reached, say, a temperature of 70 degrees C. I'm just putting a temperature. It could be 60, you can take 80, you can take 40, doesn't matter. But this thing would have happened the same, 30 to 40 to 60, 70, 80, the liquid is still there. So this was liquid, this is also liquid, and its volume increased, but increased very, very slightly. We continue this heating and come to a point we get to this point where this is still there, and this is now close to, say, about 100 degrees Celsius. Again, we have only liquid over here, and the pressure everywhere is still 1 bar. 1 bar is there everywhere. Okay, so let's see what these states will look like on a plot. So we make a plot where you have two axes there. X-axis we will plot the specific volume or inverse of density, and this side we plot the temperature. And what we will see as these 3 points is that initially, say, it was here, the volume change was very small, so the graph will not go like this, but will go pretty much steep up like that, and so we'll get a series of states like that. So here's the point that we reached at 1 bar, and all throughout this process we had a liquid. If at any state here, say take this case, instead of heating we cool it, the liquid will contract a little bit because thermal expansion, the opposite is happening, and it will come back to these states and finally come back to this state. Now what happens after we heat it beyond 100 degrees Celsius? What one sees is that the piston suddenly begins to move and move significantly. So it has come up there. And here what has happened now? This amount of liquid that was there, roughly that same liquid is there, and now here there is vapor. The temperature same. What it meant, there was heat transfer to the system, it converted some of the liquid into vapor phase. Liquid is at 100 degrees Celsius, vapor is at 100 degrees Celsius, this is at 1 bar, this is at 1 bar, but the specific volume of the liquid is this small, the specific volume of this is much larger. So what we will do on this diagram is say, well, I just plot the total volume of this. So my mass is the same, volume has increased, so specific volume, meter cube per kg, that will increase and increase a lot. without any change in temperature. So this state will now start moving along the 100 degrees Celsius line and say come over here. Okay. Then we do more heating. And what we'll see is that the piston goes up further. So it comes to another point here. The liquid amount has now decreased a little bit. The rest of it is now vapor. The liquid is at 100 degrees Celsius, vapor is at 100 degrees Celsius, specific volume has increased. Pressure, the temperature is the same, so it will be the state that is now here, we will show it by a point over there. And then we continue heating this. We reach a point where the piston has gone up over there. Pressure is still 1 bar. And in this, all we have now is a vapor, but the temperature is still 100 degrees Celsius. So this state, we can make a plot and say, okay, this thing comes over here, which means that at this point, liquid is 0 and vapor is complete, 100%. In all these cases, it was only liquid 100%. Vapor 0. In this case, as we kept heating a little bit, or as the piston kept rising, more and more of the liquid went into vapor phase. So liquid amount kept coming down, vapor amount kept increasing. The total mass of the system was still constant. Now we come to the next state. We further heat it, the piston goes up, the vapor occupies all this, but now temperature has become say 110 degrees Celsius. So now from this point to this point, adding of heat started increasing the temperature of the system. Up to this point, heating was increasing the temperature, but in this region, heating of the substance was not changing its temperature but changing its phase. So this point would then show that temperature has increased, volume has also increased, so it will go this way, and we can get a point there. And if you continue heating, these points will keep going like this. Okay, so this is some example I've taken of water, but one can do the same thing with practically any substance. We can say take nitrogen at 77 Kelvin, or say nitrogen at 1 bar pressure starting from 70 Kelvin. It will do the same thing. Take butane, take a particular pressure and start from say 10 degrees Celsius and start heating it, it will do the same thing. So all substances under certain pressure and temperature conditions will have this behavior. In a minute we will see. Instead of 1 bar, if I do it at 0.1 bar, what will happen? Or if I do it at 10 bar, what will happen? And 100 bar, what will happen? We will see those things. So now that we got all these states here, what one can do is to join them by a line. So you get one line there, a horizontal line over there, and this line goes like that. And this tells us a lot of things about the behavior of the substance. The most important thing is that from this point to this point, under these conditions, what we saw here was that pressure was 1 bar, temperature was 100 degrees Celsius throughout. Specific volume was changing, pressure and temperature, neither of them were changing. So this point where isobaric heating causes phase change to take place, or isobaric cooling causes phase change to take place, these states are known as saturated states. This is a very important concept. We will keep using it again and again. And it does not have to be at 1 bar or for water. We have examples. You get a lot of substances, including water at different pressures. It will have something like this. Then we have these 2 points, this point and this point. At this point, isobaric heating causes increase in temperature. At this point, isobaric cooling causes decrease in temperature. At this point, isobaric cooling, no change in temperature. Isobaric heating, no change in temperature. So what happens is that if you're heating, it increases the temperature. If you're cooling, it doesn't decrease the temperature. Here, if you cool, it decreases the temperature, but if you heat, the temperature does not change. This is quite different from point like this. You heat it, temperature goes up. You cool it, temperature goes down. Same thing here. You heat it, temperature goes up. You cool it, temperature comes down. These 2 points don't behave like that. So this is a point where you have vapor in this, where heating makes it temperature go up, else cooling makes the temperature remain same but causes phase change. This is called a saturated vapor. Or sometimes dry saturated state. That is one. And this state is state where the substance is called, this is a saturated liquid. So saturated liquid means isobaric heating will cause phase change. Saturated vapor means isobaric cooling will cause phase change. So we have now 2 limits that have come up. And then you have all states in between here where the pressure and temperature were both same, specific volume kept increasing. All of these are saturated states, or we may call it wet saturated or just plain saturated state. And here, all these states, this substance is said to be a superheated vapor. And these states, this is called either a subcooled liquid or a compressed liquid. So several important things have come out from this small discussion. These are all subcooled liquid or compressed liquid states. This point is the saturated liquid state. This point, the saturated vapor state. In between, all these are wet saturated states. And this point, all these are superheated vapors. Okay, now let's take this problem further and say, keep heating it, what will happen? Well, what this picture tells you that it will keep on going up this way. Specific volume will keep increasing, temperature will keep increasing. The vapor becomes more and more superheated until finally we say it is starting to behave like a gas. And if you heat it even more, it will start to behave as an ideal gas. And further on, either of 2 things can happen. The continuum hypothesis may break down, or the substance may begin to dissociate. O2 can break into O and O atoms. So we will not go to that point. But that's what will happen if this heating were to have continued for a long time. Okay, so we have introduced 5 very important concepts: subcooled or a compressed liquid, superheated vapor, wet saturated state. In the wet saturated state, as you can see from here, this whole state is called wet saturated, but the top part was saturated vapor, and the lower part where the liquid was, that liquid was saturated liquid. So actually this is a mixture of this state plus this state. It is no new state as such. Okay, I will come back to the question. We are just about to come there. Yeah. Okay, so this has happened here. And now what happens is, In the saturated state, the substance has an interesting behavior, and what we saw was that with heating, pressure and temperature were the same, but specific volume kept increasing or decreasing, whichever way you're heating or cooling it. Which means that if I say that this substance, I have two things, two containers, one is got this much volume, the other has this much volume, and this has this much liquid and this much vapor, and this has this much liquid and this much vapor, and both are at the same pressure and temperature P and T. And so if say I know the pressure and temperature here, tell me what is the specific volume, we now have a problem. Because of the same pressure and temperature, this specific volume is also possible, this specific volume is also possible. So what it is telling us is that P and T are just not enough by themselves to tell us everything about the system, and what we get is that in saturated states, pressure and temperature are not independent of each other. There is a one-to-one correlation between pressure and temperature. But that's only the saturated state. That means if you say, well, what is the temperature? Say, well, 100 degrees Celsius. Then we can look up data that is already there and say, look, the saturation pressure at 100 degrees C is 1 bar. So we are introducing a new concept that in a saturated state, the pressure and temperature are known as the saturation pressure and saturation temperature. And conversely, we can say that at 1 bar, what is the temperature at which phase change will start taking place? Well, for that we say, well, tell me what is the saturation temperature at 100 degrees sorry, at 1 bar, and the answer is 100 degrees Celsius. So by knowing the pressure, we can know the corresponding temperature at which a saturated state can occur, which means that it could be either saturated liquid, saturated vapor completely, or any mass mixture of these two. So this is what is happening. And now we say, well, what happens in the other cases? So for this, one only needs to go to a table, and these properties are well documented, and you say, look, for this material, this is the pressure, this is the saturation temperature. And the pressure in this case is 1 bar. In a minute we will see what happens if it is 10 bar, 0.1 bar, or if the substance is different, everything will fall in place. What we will define now is, well, compared to the saturation properties, what can I say about subcooled and superheated states? So what you are seeing is this, that on this chart, for a state which is over here, the temperature T, or say we will call it, say that T star, this temperature, and compare it with the saturation temperature at the same pressure. Saturation temperature at 1 bar, then this T star we are comparing in this case with 100 degrees Celsius, and we know from looking at it, T star is less than 100 degrees Celsius, and that's the reason why this is called a subcooled state, or subcooled liquid. That means for the given pressure and temperature, the temperature is less than the saturation temperature at that pressure. And very clearly it becomes that all the water we use and drink, its temperature is 25, 30, 35 degrees Celsius. That would be here. The pressure is 1 bar. The pressure saturation temperature at 1 bar is 100 degrees Celsius. And so what we are dealing with every day, what we call water is actually subcooled liquid water. When water begins to boil, we say, well, what is the temperature there? And at that time we'll say, well, now my water is boiling, my T star is now 100 degrees Celsius. And that's why you keep seeing bubbles coming out, because its temperature is not going up. You can make the gas stove or the electric heater as big as you want. The temperature is not going to go up, only the liquid will keep becoming vapor, and finally everything will disappear. So what we have produced at that point is a saturated state, or a saturated liquid. That saturated liquid became saturated vapor and went and diffused into the atmosphere. That's what happened. Now we look at it in another way, and we say, what is the pressure here compared to the saturation pressure at 40 degrees Celsius? Okay, so we have T star and 1 bar, and say T star was 40 degrees Celsius. Then we say, well, what is the saturation pressure at 40 degrees Celsius? And you look up the tables, and this, my guess, is of the order of like about 25 or 20-25 kilopascal. I'm just putting a number there. It's of that order. This is not the exact number. Now we compare this and this. This is less than the actual pressure at which it is. That means you have compressed it, and that gives the name, same state, another name, compressed liquid. So compressed liquid and subcooled liquid mean the same thing. In one case we are comparing the temperature with the saturation temperature at the pressure. In one case we are comparing temperature with saturation pressure at that temperature. So that's a compressed liquid. And we take that analogy a little further, and we come to the superheated vapor state. And what one sees here is that in all these cases the temperature is more than this temperature. So if the temperature T star at any state here is compared with the saturation temperature at that pressure at 1 bar, this temperature is more than the saturation temperature. This tells us that this is a superheated vapor. So it's a very simple thing, that if someone says I have vapor at 1 bar and 200 degrees Celsius, tell me what is the state, then you would say, look, 1 bar, the saturation temperature is 100 degrees Celsius, the vapor that you have is 200 degrees Celsius, the superheated state. Okay? So it's the superheated vapor. This is the way to find that out. We can define one more parameter here as the delta T, which is T star minus the saturation temperature at that pressure, and this is defined as degree of superheat. And similarly, another delta T of subcooling, this is delta T superheated. If this is T saturation at T star minus T star, this is degree of subcooling. And in any saturated state, the pressure and temperature will be the corresponding saturation properties of each other. We can say one more thing now that we have looked at specific volume. In this picture, we will denote the saturated vapor phase by a subscript F, and this by a subscript G, fluid and gas. So specific volume at this point was this, specific volume here was this, specific volume here is this. This is called Vg, this is Vf. Now these are fixed properties that once you say I have 100 degrees Celsius, what is the specific volume of the saturated liquid? It is Vf, that is known in tables. First, what is the specific volume of the saturated vapor? In that case, Vg, that is known in the tables. So we can, on that basis, we know that all wet states will have specific volume in between these two parameters. So another way to decide whether it is a subcooled liquid or superheated liquid is that if the specific volume given is V star, if V star is less than Vf, that means it is on this side, this is subcooled liquid. If V star is greater than Vg, superheated vapor, and if Vf and Vg are the limits within which V star lies, then these are all wet saturated states. Or simply we can even just say a wet state or a saturated state. In this region, superheated region, pressure and temperature are independent properties. In subcooled region, again pressure and temperature are independent properties. In this case, they are not. And this is the big change that has happened from what we have learned. And we have to learn how to handle this, because all your power cycles, all refrigeration systems, everywhere we encounter a saturated state. So it's very, very common. Okay, so let's now define one parameter by looking at any saturated state. So we have a system, a closed one. It has got certain amount of a liquid and certain amount of vapor. And this is what is different between different saturated states, is the proportion of these two. And so we have to define something which tells us how much of liquid is there, how much of vapor is there. And for that we will define a new property which is called the dryness fraction, or also known as quality. The symbol is X. It is defined as mass of the vapor divided by the total mass, which is mg upon mf plus mg. Okay, so this is a new definition that we are now putting in, and let's see, can we express it in terms of the specific properties. And it's a small little exercise that we can do by saying that the volume of the liquid is capital Vg, volume of vapor, vapor is Vg, fluid is Vf, its specific volume is Vg, its specific volume is Vf. And by definition, we know that mg, this is mass, this is volume of the gas divided by specific volume of the gas. mf similarly is Vf upon specific volume of gas. So remember that we are just looking at two things here. This is saturated liquid, saturated vapor. They are in thermodynamic equilibrium. So if we do this thing and exploit the fact that V is equal to Vg plus Vf, and then we substitute this into this, we can get that the total volume is mg Vg plus mf Vf, and we by the definition of x, which is mg upon mf plus mg, we can then put into this, do a little bit of simplification, and what we get is that x is equal to 1 minus x times Vf plus x times Vg. That tells us, oh sorry, this is V. Okay, I will define V here. V is V total upon M total. What it means is that if this is the whole system, then the dryness fraction of this is X, and the specific volume of this is given by this expression. Over here, X is equal to 0. It's a saturated liquid. Over here, X is equal to 1. It's a dry saturated vapor. But taken together in this whole system, you have a dryness fraction which is in between those two numbers. So you have X will always be between 0 and 1. X equal to 0 means saturated liquid. X equal to 1 means dry saturated vapor. So that's the independent property that we were looking at. We can get it from this. And what it tells us is that now for saturated state, T and P are not independent properties, but T and V is okay. Because if it is a saturated state, no matter where it is, there will always be one unique point on this diagram. So if that particular point happens to be here, you know that this is the specific volume, this is the temperature, and you can calculate X from here, and we will see how to calculate all the other properties. Similarly, P and V, these are independent properties. And one can do a similar type of a argument, and we can show that H of the mixture is 1 minus X times HF plus X Hg. The specific enthalpy can be calculated that way. Specific internal energy, you do exactly the same thing. Specific entropy, we do the same thing. So what we have come to a point now where we say that I had independent properties called P, T, V, and now we have added X, U, H, S to that. And what we have said is that any two of this is applicable only for saturated state. So with the superheated vapor, we don't say X is equal to 1. X is not defined for states other than the saturated state. So if it is, in any case, for saturated state, that is defined, and these two are interdependent. They are one and the same. Otherwise, in general, any two properties out of this will completely specify the state of the system. So if I know U and H, good enough. state is uniquely specified, we can go back to the property tables and get all the other values: pressure, temperature, specific volume, specific entropy. If P and S are given, same thing. It's an independent, there are two independent properties. The state is completely defined. We can calculate all the other properties. If T and H are given, again, the state is completely defined. We can get all the other properties. The care that has to be taken, as we have seen now, is if it is a saturated state, P and T are not independent properties. They are one property, and either of them with V, or either of them with U, or either of them with S or H, they will completely define the system, or with X. So they are okay. The only thing that is not okay is P and T. V and X is okay, X and H is okay, X and S is also okay. These are all independent properties. But then X is only for saturated state. Let me say that again. Okay, so now we do the same experiment we did earlier. But we do it now, instead of at 1 bar, we say we'll do the experiment at 10 bar. And then we'll do it at 100 bar, 200 bar, 300 bar, 500 bar pressures. What happens? So that's what we will make the plot now. This side is V, and this side is T. And the first chart that we got was at 1 bar. So I'll just reproduce that over here. This was 1 bar. Now what will happen if you do it at 10 bar? Well, let's say that if I start from the same temperature, 40 degrees Celsius, and increase the pressure to 10 bar, 20 bar or something like that, those states will go this way. Okay, I am exaggerating a lot, but in reality the change of volume of a liquid is very, very small. And you can see the plots, there's practically no difference between these densities. But just to illustrate the point, I pulled them out. In reality, they are not that far off. Simple reason, in school we have learned liquids are incompressible. That's the manifestation here. Now we heat this liquid, and what we see is that this thing goes up here, and the temperature at which the phase change begins has now increased, and the specific volume at which it is happening has also increased, and it changes phase, and it is somewhere here that it becomes a completely a vapor phase, and then from here it goes off. So this is 10 bar. In between these, we have all the saturated states. So that's what 10 bar did. Vf moved, became bigger. Vg decreased in quantity. The difference of these two, Vg minus Vf, this is often referred to as Vfg. And similarly for specific entropy, specific enthalpy, and specific internal energy. You can call this as specific volume of evaporation, or specific enthalpy of evaporation, what we learned in school as latent heat. So what it tells us is that this thing that was latent heat, which was that much, has now become this much. Specific volume has also gone down. Now what happens if we increase the pressure further? Go to 100 bar. It comes over there. Then you have a series of states that come somewhere there. and then you have the same behavior there. So 10 bar, 100 bar, now let's go to 200 or some 200 bar. At 200 bar, this will come up steeply, come up over there, and this will be here, and from here the states will go off there. So this difference in specific volumes of vapor and phase keeps decreasing as the pressure increases. 10 bar, 100 bar, 200 bar. And then there is unique pressure for every substance at which this part becomes 0. That means this curve, which is coming like this, has a point of inflection and continues like this. That means at this point, the slope is 0. This is what is called as the critical point. This is a unique property of every substance, and it's all tabulated that the critical point, this temperature is called the T critical. The corresponding pressure at which it happens is P critical. The specific volume at which this happens is V critical. Specific enthalpy at which at that point is H critical. Entropy is S critical, and like that. So this is unique point. And what it tells us is that if you do this isobaric heating at pressures for water, this is about 220.9 or 220.6 bar, something like that. And at even higher pressures, at 300 bar, this line will go up and just continue like that. It will never come to a zero slope. So this is the all states where pressure is more than critical pressure, and above this point temperature is more than critical temperature, and here we don't call it a compressed liquid or a superheated vapor, we just call it a critical fluid or a dense fluid or a supercritical fluid. Power stations, coal burning power plants that are being built now or have been built in the last 5-10 years in India, they all had steam in the supercritical state. 20 years back, pressures were less than the critical pressure. Those were all subcritical units. And the difference was that in a subcritical power plant, you got to design some part where the phase change takes place. In a supercritical plant, this issue is not there. And by thermodynamics tells you a very simple thing, this has a very big implication on heat transfer and the mechanical design of the boiler itself. There are completely different philosophies for this type of a boiler versus this type of a boiler. The first steam locomotives that operated, their pressures were like 3 bar, 4 bar, somewhere here. And over the last 100, 120 years, these pressures have continuously gone up, temperatures have gone up, where today's temperatures are of the order of 565 degrees Celsius, which is the supercritical temperature, and this is being pushed to 710 degrees Celsius in power plants that will be built maybe 7-8 years from now. So whole thermodynamics is what is driving this whole thing, because the efficiency goes up, the cycle efficiency. So this is the type of picture we get, and now what we can do in this is that we join all these points These are all saturated liquid states at different pressures. So we can say that these are all representing dryness fraction 0. Or this is a saturated liquid line. And similarly, we can join all these states on the other side. These are all the states where X is equal to 1. Dry saturated vapor, saturated liquid. In between this are all the wet states. Okay, so what it tells you that as you go from left to right, X goes from 0 to 1. So in this, one can draw lines which are somewhat like this, and say, well, these are constant dryness fraction lines. X is equal to 0.6 is this much, X is equal to 0.7, X is equal to 0.3, they are like that. Okay, all the definitions that we had are valid for all this discussion. This is a saturated liquid. Left of this is a compressed liquid. This side is superheated vapor. In between, we define the dryness fraction. And the top, this is the critical point. So the upper limit of some sort has been set in the properties. As I'm saying, all of this is a huge exaggeration. In the notes, I've given some plots where all of this just becomes very, very small. You can see that in books also, that the effect of pressure on specific volume is very, very small. So that's, as an approximation, one can even say that water at 40 degrees Celsius and 1 bar has the same density as saturated liquid at 40 degrees Celsius. Okay. The next question comes up, what happens below this? If I decrease the pressure to 0.1 bar, 0.01 bar, will I get the same behavior? And the answer is that yes, you will get the same behavior until we reach a point which I will call here, where these lines will end, and this is what is called the triple point. Okay, so the critical point on the top, the lower limit of this is triple point. And for water, the triple point again is like a critical point, is a unique value. Triple point for water is 0.01 degrees Celsius. Triple point pressure is 0.6119 kPa. And you can get the specific volume also. So what the triple point line and all these states, they are all triple states, triple point states, which means that there will be solid plus liquid plus vapor existing on this line. And if you go to temperatures below the triple point temperature, there is no possibility of a liquid. You will only have solid plus vapor formation. Okay, so this is one thing that comes up, that there's a limit at the bottom, the triple point, at the upper, a critical point. If temperatures are between these two values and pressures are between the corresponding triple point and critical point pressures, only those conditions we can expect to see a wet saturated state. It is not necessary that it will always be there, because at this temperature, if we have this pressure, it is a superheated state. But if the pressure is between the, so if the given temperature is between T triple point and critical point, and triple point pressure and the given pressure, then we can expect a saturated state to be formed. Saturated liquid plus vapor state. At temperatures below the triple point, we get saturated solid plus vapor phases. The other points where you get solid plus liquid phases. Okay, so that becomes the big picture of the what is called the TV diagram. And it gives us the ability to tell what will be the state of the substance once two independent properties are known. So if we can locate that the state is, say, here, we know it is a wet saturated state, we can figure out where is the temperature, what is the specific volume, and then calculate all the other properties also. If the state happens to be here, we know this is superheated state, what is happening. If the state happens to be here, you know this is a supercritical fluid or a dense fluid, we know what the specific volume, entropy, everything else is there. So this helps in a very graphical way to very quickly visualize what states to expect for a given pair of properties, provided specific volume is one of them. Okay, so that is one thing that has come out. The real thing looks like this, what I have put in the notes, this would be with you. Okay. Yeah. So what I showed qualitatively, this is the actual numbers on this. And the specific volume I have kept on a logarithmic scale, whereas temperature is a linear scale. And what you see is what I just explained. This is at 1 bar. This is at 5 bar. This is at 50 bar. Then you have 220. This is 220 bar. And the top one, 300 bar. And so these are all the saturated vapor states. These are all the saturated liquid states. And what you see here is what I was just mentioning, that the way I made the drawing qualitatively, my freehand, is quite unrealistic in what the actual numbers are. You can see here all these points are practically on one another, that the effect of pressure all the way to 300 bar versus 1 bar, there's hardly any difference in the properties at low temperatures here. You only here that you start seeing some difference, but 100 degrees Celsius, the effect of pressure has very, very little effect on the specific volume. That's why all these have collapsed on one. These are all the saturated liquid points, and you could have, I didn't draw the complete thing, but you can draw this point here, get the saturated vapor line, saturated liquid line, and there is the critical point. The next thing is that this is typical of all substances. You take oxygen, hydrogen, nitrogen, ammonia, sodium, any material, they all behave like this. So what we have learned is basic aspects which are very, very generic and are applicable to every material.